Hello and welcome to the presentation of our paper called A Comparison of Abstraction Heuristics for Rubik's Cube. My name is Clemens Büchner and this is joint work with Ferber, Jendrik Seipp and Malte Helmert. Rubik's Cube is a perfect example of a classical planning problem. We start at a given initial state and we would like to reach some goal, here the cube where all faces only show a single color. To change the state, we can apply so-called operators. In the case of Rubik's Cube, this is rotating one of its faces. Repeating this process amounts to a huge state space. And now the goal is to find one of the paths through this state space that leads to the goal state. Since the state space is so large, this is not feasible by only using brute force. One way to deal with this problem is using abstractions. Abstractions combine several states of the concrete world into so-called abstract states. Now the problem is much simpler and finding a solution to the goal now is easier. This information can then be used to solve the original problem. Indeed, the state-of-the-art for solving Rubik's Cube optimally uses projections, one class of such abstractions. In recent years, abstractions, a lot of research has been put into more general abstractions than projections. This raises the question how these methods perform on this problem. In this paper, our contributions are a model of Rubik's Cube that can be used with today's general problem solvers. We also show a way how Cartesian abstractions can be generated in the presence of conditional effects. Last but not least, we evaluate all these abstraction classes on our problem of Rubik's Cube. So let's dive into this model. We use 20 variables, one to represent each of the corner and edge cubies of Rubik's Cube. The domain of each such variable represents the positions and possible orientations of each cubie. So consider, for example, this corner cubie. At this position, it can be at 3 different orientations, but it can also be at each other corner of the cube. So that's the domain of this variable. Our model uses 18 operators, and this is 3 per face. One is turning clockwise, another one is turning counterclockwise, and the third is doing a half turn of the face. All of these operators have no preconditions, which means they can be applied in any of the states. The effects of these operators are conditional, and what they say is for each cubie at each possible position and in each of its possible orientations, how it changes when this operator is applied. Overall, Rubik's Cube has a set of 4.3 times 10 to the power of 19 reachable states. The current state-of-the-art for solving Rubik's Cube optimally uses pattern database heuristics. What happens here is the variables are split in 2 groups, the corner and the edge cubies. These denote simpler problems that can be solved completely, and the goal distances for these are stored in a lookup table. Once we would like to search for a solution of the original problem, we use the maximum of the corresponding entries in the lookup table as the heuristic in an IDA star search. This paper was published 25 years ago, and in the meantime there has been put a lot of research into more general abstraction heuristics. So let's have a look how these abstraction heuristics compare. For this, consider this much smaller example with only 2 variables, one which can have values a and b, and another which can have x, y, or z. We've already looked at projections, which in the end lead to pattern databases. So what these do is simply ignoring sum of the variables, or in other words, putting all states together that agree on a subset of the variables. Domain abstractions are a bit more general because they allow for each variable to decide which values I would like to distinguish. Cartesian abstractions allow even more freedom because they allow us to distinguish values of a variable in some parts, but not in other parts. Finally, merge and shrink abstractions allow to combine states with each other that have absolutely nothing in common, which is the most general among these. Since we are not aware of any techniques to generate domain abstractions in a principled way, we don't consider them in our analysis. For projections and merge and shrink abstractions, there are ways to deal with conditional effects. But this is not the case for Cartesian abstractions. So let's have a closer look at how Cartesian abstractions are generated. The most common technique uses counterexample guided Cartesian abstraction refinement. What this does is it starts with the coarsest possible abstraction and then iterates the following process. Find an abstract plan, here the empty plan, then execute it in the original problem until you find a flaw or a solution. Since here we did not arrive at the goal state of the original problem, we need to find out why this did not work out. And of course, one explanation is that the second variable does not have the value c already. So we split off all the states where it has this value from those where it doesn't. We then start over and find an abstract plan for this problem. Again, this fails when we try to execute it in the original, because now the precondition of one of the operators is not yet satisfied when we try to apply it. So again, we split off states where the precondition is or might be satisfied from those where it is not. Repeating this will eventually lead to a very fine-grained abstractions on a solution path. Now, in the step of refining, we need to know what was the reason why we failed to execute in the original. And here, for example, we would use regression to do so. With regression, we get all the states where the operator could have been applied, and then we can separate them from those states where this wasn't the case. However, there is a problem, and namely this is that regression through operators with general conditional effects does not lead to a Cartesian set, which must hold in order to keep the abstraction Cartesian. However, Rubik's cube denotes a special case here. And this special case is that each effect, like the new position and orientation of a cubie, only depends on its old orientation and position. So it doesn't really matter what all the other cubies look like. For this single cubie, this is all we need to know to see what the effect of a certain operator is, or to see where a certain operator could have started to end up with this value. Now let's have a look how the different abstraction classes performed in our experiments. We generated 200 Rubik's Cube problems of increasing difficulty. Looking at the coverage shows that pattern databases were able to solve the most out of these 200 tasks. If we look at the plot on the right, we see how many states have been expanded by each of the techniques. We plot against pattern databases, which means that the data points below the diagonal are those where the heuristic guidance of the other technique was better, whereas above the diagonal means the opposite. We can observe that with Segar we find almost a perfect heuristic in most of the cases where it was able to solve the problem. These are all the points that lie on the bottom line, where 0 states were expanded. However, at a certain difficulty level, the number of expansions goes up significantly. We think that this might have to do with the cutoff time for generating the abstraction in the first place. Once the algorithm runs out of time for refining the abstractions, it will have a very fine-grained abstraction around the initial state, but at some point it does have no clue how to get closer to the goal anymore, and the search becomes almost blind. So what have we learned today? We now have a new benchmark set of Rubik's Cube problems in the SAS+ formalism. Furthermore, we have adapted the Cartesian cigar algorithm to work with factored effect tasks. It yields almost perfect heuristic values up to a certain difficulty. Yet, fewer tasks are solved by the more general abstraction classes than pattern databases. In the future, we would like to consider more permutation domains besides Rubik's Cube for our analysis and compare the results between each other. Moreover, we would like to extend our work with ways to generate domain abstractions, which is a missing piece of the puzzle in this analysis. Thanks a lot for your attention. We're looking forward to the discussion.